Dear students, welcome to this first video for our applied data analysis class. And to be honest, for you this is the first video, but I had about 50 attempts to record this in a flawless fashion, and now I will just do it. I don't care anymore if it's perfect or not, and I hope you will be forgiving in this regard. The title of this video may sound somewhat peculiar to you, and it's termed Understanding the Loss Function. And the loss function is at the core of all inverse methods and all optimization methods, and it's also at the core of many machine learning techniques. And so I think it's worthwhile that we take a little bit of time to clearly define the loss function in a mathematical sense. This may be more theoretical than what you're used to, but do not worry, in the accompanying exercises I will provide you with plenty of applied examples where this theory will be filled with applications in an earth science context. What you will need to know as a mathematical background to understand this video completely is rooted in linear algebra. So you need to know what a matrix is, how matrices are multiplied, how you multiply a matrix with a vector, and what the norm of a vector is. If you do not know these things, do not hesitate to watch the video anyway. Then go back to the literature and specifically read up on the things that you didn't know, and then just watch the video again. After all, it's a video and you can do with it as you please. Okay, so let's dive in. What I show you here is a benchmark dataset quantifying the increase of atmospheric CO2 since the 1960s to today. This curve is called the Keeling curve and it's measured in Hawaii. And a typical question that you may ask seeing this kind of data set is, what's the average trend of CO2 increase that we have seen over this time period? And if you ask this question, you're essentially asking, what's the best fitting line through this data set? And a line has 2 degrees of freedom. One is the slope, steeper slope, less steep slope, and the other one is the y-intercept, and the y-intercept essentially determines the offset of this line. So we have 2 free parameters that we need to find. If I write this down more mathematically, we describe this function with the slope m and the y-intercept c. And more specifically, we would like that this function describes the observations. So for a particular point in time, here described with xk, we want this function to predict what the atmospheric CO2 content was back then. So in an inverse framework, y equals mx plus c is our forward model, and if we know the parameters of this model, m and c, we can easily predict the data. The inverse problem is we have some observations. What is the best m and c describing these observations? And ideally, I would like that our optimized forward model is in line with all of the observations we have. And if I request that for each and every data point, I end up with a system of linear equations. For each data point, we have one equation. And here I introduce the number NO, which marks the number of observations. Why is this system linear? Well, it's linear simply because we don't have any nonlinearities in here. So there is no squares, no cosines, no exponentials. And if this is the case, then I can rewrite the system of linear equations in matrix forms. And this is what you end up with. You have a matrix, here G, that you multiply with what I call a parameter vector, because here are our unknown parameters, m and c. And on the right-hand side, we have our observations, yn to yno. And just take a minute and make sure that you understand what's going on here. Up here is our old linear system of equations. Here it's rewritten in matrix form, and you can easily reproduce the first line here, x1 times m1 plus 1 times c equals y1. And why would we do that? Well, this is the first step of generalizing our results. So in this form, we don't only treat problems in form of linear regression, but we treat all linear problems that can be written in this way. And there are a lot of problems that can be written in this way. And so once we have the system described as gm equals d, and note that I introduced here a different parameter, np, which is the number of free model parameters, which is 2 in terms of linear regression, then we just want to solve this system. So in essence, we are looking for an inverse of the matrix G so that we can move G over here to the right side and isolate the unknown model parameter vector and solve our system. And so the question is, does an inverse of the matrix G actually exist? And the somewhat dramatic answer is that no, it does not exist. And you can show this fairly easily if you go back to our example of linear regression. You can argue in a graphical sense. There is simply not one line that will connect all these data points. And you can also argue in a mathematical sense by just picking out 3 random observations from our linear system of equations and solve for M and C in this particular case, and you will very quickly show that those equations are inconsistent. So what can we do about that? Well, let's go back to the standard form of our problem, and what I will do next is I take this data vector here to the left-hand side, and then I request that the difference between our forward model and the observations is small. It cannot be 0, we've just shown that, but the best we can hope for is that the difference is small. What does this look like in the example of linear regression? Well, in this specific case, we would request that the prediction of the model at time t minus the observation is small, and this should be ideally the case for all of the observations we have. So it means that if the sum of these differences is small, that would be a good thing. However, there's one catch. In this specific example here, the difference between observation and model is positive, whereas over here, the difference between observation and model is negative. And those 2 terms could cancel out if we just take the summation. In order to avoid that, we request that the square sum of all the differences between model and data is small. There are other options. We could also take, let's say, the absolute values, and sometimes that is justified. But in most cases, you will request that the square sum of all the differences is small. And if you do that, you arrived in the area what is called ordinary least squares. How does this square sum look like in the specific case of linear regression? Well, it looks like this. Here we sum over all the observations that we have. And what do we sum up? Well, the difference between the model prediction and the observation at time xk. And we have to square that to avoid this averaging that we've just discussed previously. Okay, and this is the essence of the loss function. And I hope you understand why it's termed a loss function, because it somehow quantifies by how much our forward model misses the data. Other people call it the cost function because they want this sum here to be small. And if the costs are high, that's not very good. So you want to have a low cost. Other people call it the objective function because the objective is to find a set of model parameters here, M and C, that minimizes this sum. Can we generalize this to other linear problems? Yes. For this, we go back to the standard form Gm equals D. Take the observations to the left-hand side and then quantify the misfit between forward model and observations in the model data misfit vector. And ideally, we would like that all of the components in that vector are small. And in the language of linear algebra, that means that this vector should have a minimum length. And the length is defined as the norm of the vector. And the norm you can calculate with the square sum of all of the individual components. And I spelled this out for you over here, and this term may look a little daring to you, but I'll digest it for you, and there's really no magic hidden in here. Let's start with the square. This makes sure that we are squaring the model data differences. This is the sum again over all of the observations. Here are the observations. And now you maybe wonder about this term, but this term is essentially the model prediction at time k for these observations. And if you think about it again in the context of linear regression, this would be the mx plus c. So the number of model parameters would be 2, and this sum would just result in the 2 terms mx plus c. Okay? But we've now just written it in a much more general form for all linear problems. But what if our forward model is not linear? Well, then we can still define the loss function, and in that case we just don't describe it with a matrix because we can't, it's a nonlinear forward model, but still we want the differences between the forward model and the observations to be small. And this brings us close to the end of the video, and I'm very happy about that, because it took me another about 20 to 30 takes to even arrive at this point. So I hope I can now finish this off smoothly. So what have we done? Well, we defined the loss function for the specific case of linear regression, and then it will look like this. We also generalized this for all linear forward models that can be written in the form Gm equals D, and then the cost function looks like this. If our forward model is nonlinear, the cost function will look like this. In all these cases, we seek to minimize the cost function, which means we seek the parameters which minimize the misfit between our forward model and the observations. And in the videos to come, which I'm totally not looking forward to, we will develop techniques, and we will start with techniques for linear forward models and then dive into techniques for nonlinear forward models. And in that sense, you can hopefully look forward to many more videos if I manage to do that, because it's really taking all my energy. So, goodbye.